Est-ce que là, tu m'entends? Est-ce que dans le Zoom, tu m'entends?
Le Zoom, je ne me suis pas encore connectée.
Dans le YouTube, tu m'entends?
Bah, justement, c'est ça que j'ai pas. Je vais aller sur une autre vidéo YouTube pour voir. Est-ce que je vois la souris bouger? C'est bon? C'est juste une attente.
Ok, très bien. Est-ce que dans le Zoom, tu m'entends? Ça va être
à quoi?
Tu m'entends?
Bah, justement, c'est ça que j'ai pas. Si je te parle,
Là, si tu me parles,
Sinon, la tienne aussi, elle va se faire.
Ouais, moi je suis une privilégiée, mais il y a un ordinateur au niveau.
Amélie Gruel.
Si vous voulez qu'il y ait tout le jury, il faut que je sois là.
On peut s'asseoir sur les sièges jaunes apparemment.
Ah oui. Ouais.
J'ai la Elisabetta Chica, c'est
Ah
le
ouais.
jury.
Nous, on est trop. On va choisir les
Hello.
Hi,
Agnès.
Hi. Nice to meet you.
Ah, ils sont là.
can you hear me?
Yeah. Can you hear me?
Oh, yes.
Perfect. Okay. Right. I'm going to start sharing the slides and everything so it's a better camera. And you're the first one here, so we're waiting for the others.
Okay, but there was an email about the YouTube link.
Yeah. Oh yes, I did not send you.
I didn't receive the link.
The YouTube link. Yeah, I'm going to send you. I forgot to send it to you. I'm sorry.
No problem.
Okay, I'll send it right now, and I just shut off the mic because all the people in the room may be a bit noisy for now. But I'm sending it right now. Thank you for letting me know.
Et je vois très bien avec
Laetitia va envoyer le lien à Elisabetta.
Je
Okay.
l'ai envoyé par mail le lien. Si elle était dans les. Si elle était dedans.
Voilà.
Est-ce qu'elle était dans les.
Non, elle n'est pas dans ma liste.
Hello.
Elle est dans le.
Laurent.
Hi,
Elle est dans les signataires de.
Okay, someone is going to send you the YouTube link.
thank you. Thanks a lot.
Bonjour tout le monde. Hello. Can you hear me?
C'est bon? Ah, hi.
Hello. Can you hear me? Yes?
Yeah.
Okay, good.
So we have everyone, I guess.
Everyone?
Who's joined you. Yeah. Yeah. So there are also members of the jury that are here. You cannot see them because the camera is on the side, but they can. We will have the camera going over to see. Oh yeah, okay. On your side. Hi, yeah, just saying hi. Yeah. Okay, perfect.
So before starting, I would like to check with you that you can hear us correctly. So Elisabetta, can you confirm? Okay, all of you. Okay, that's perfect. So you will have the screen and the presentation that will be shared in a few minutes. I would like first to present the jury, the composition of the jury for the presentation that will be held today for this for the thesis of Amélie Gruel. So in remote, we have Elisabetta Cicca, professor at the University Cicca, sorry. That is full professor at in Netherlands at Koninginnenhof. It's written like that in the report. We have also Timothée Masquelier, CNRS Researcher Director at CERCO, France. Chiara Bartolozzi, Senior Researcher at IIT in Italy. And Julia Sandamerskaya, Senior Researcher in Switzerland. And here locally, Michel Panavoine, Emeritus Professor at LEAD in France. There are also, so you are not written, Laurent, on the composition of the jury. But for your supervisors were Jean Martinet, full professor at Université Côte d'Azur here in laboratoire, yes, at laboratoire I3S, and Laurent Périnet, CNRS Researcher Director at University Aix-Marseille, Institut des Neurosciences de la Timone. Riyad Ben-Osman, Research Director at Meta, will be with us during the presentation. So we will come in a few minutes. And I am Bonhomme Miramon, full professor at LEAT Laboratory here in University Côte d'Azur, and I am glad to be the president of your jury today. So you have 45 minutes for your presentation, and then we will go to the session of questions.
Perfect.
So we can start now.
Okay. Just share the screen. Can everyone with the remote see my screen? It's okay? Perfect. Hi everyone, my name is Amélie Gruel, and today I will be presenting you the work I did during my 3 years PhD on the subject of spiking neural networks for embedded event-based vision. And first of all, I would like to thank every one of you for being here today, and especially all the members of the jury for accepting to take part of this defense, either remotely or here at I3S. And I would also like specifically to thank Chiara, Timothée, and Michel for all the feedback that you gave me on this PhD. So, Leonardo da Vinci famously said, "Go take your lesson from nature, that's where of you to lies." And the human beings did answer to this advice by creating many technologies such as airplanes, Velcro vaccinations, and more recently, by creating artificial intelligence. This technology is the development of computer systems able to perform tasks normally requiring human intelligence. Since I'm doing a PhD in computer vision, I'm going to specifically focus on visual perception tasks. And for this task, there were recently a lot of neural networks that developed with performance that kept increasing. if we take a look at the results that we obtained with those neural networks applied to the ImageNet dataset, we can see that there is a huge boom in the performance that even got better than the performance of trained human annotators in 2016, and even outpassed the performance of optimistic human performance in 2018. And this is mainly thanks to the application of the first deep learning models to this dataset, such as the famous model of AlexNet. So when you look at those results, you think, okay, we took information from neuroscience to implement neural networks, but should we still continue to do so? Because we have results that are way better than the one obtained by human beings. Well, in this PhD, we believe that yes, we should still draw inspiration from neuroscience, and I'm going to tell you why. If we take the famous example of ChatGPT, this big deep learning model used during training an energy consumption of 1.3 gigawatt hours. In other terms, it corresponds to 550 tons of CO2 equivalents, which is the same energy consumed if you do 500 Paris-New York plane round trips, which is huge. If we take a look at other numbers, such as the impact of digital world on the environment that were measured in 2019, we can see that these digital worlds were responsible for 4% of greenhouse gas emissions and consumed 4% of primary energy in 2019 only. If we compare those neural networks that are able to do really a specific task to the human brain that is able to do a lot of functions simultaneously, such as making sense of a complex changing world, planning complex actions, navigating our social environment, entreating the minds of others, and learning and remembering across our entire lifespans. We can see that this human brain is able to do all of this using only 100 billion neurons interconnected by 100 trillion synapses with a power budget of only 20 watts. So if we compare those numbers together, we can say that yes, computer science will really gain if we continue to draw inspiration from neuroscience, especially when we take a look at the energy consumption part. My PhD that took place within the scientific context of the Aprovis 3D project. It is a European project that reunited all the labs in Europe with a common use case of performing autonomous tracking and monitoring of the Mediterranean coastline in order to monitor the erosion of this coastline. So how do we want to implement this autonomous tracking? We take as input a video of the coastline of the Mediterranean that is recorded by an embedded camera on the drone, and then this data is processed by a bio-inspired neural network on the same drone in order to obtain the direction the drone should take to follow this coastline. And what is interesting is that we are not using an RGB standard camera, but we are using an event-based camera in order to perform both neuromorphic sensing and processing on board of this drone. But what is neuromorphic? Well, neuromorphic computing was introduced in the 1980s by Professor Carl Vermeet at Caltech, and it is a new technology that is a combination of biology, electrical engineering, computer science, and mathematics to create artificial neural networks able to handle information as a human brain and nervous system would. So to perform neuromorphic computing, we can do neuromorphic sensing and processing. So there are a lot of neuromorphic sensors that can do either sighting, hearing, smelling, tasting, or touching. And there exists a lot of different ways to do neuromorphic processing, such as the spintronics, the in-memory computing for deep learning, the spiking neural networks, and the photonics. And in this PhD, we are going to specifically focus on two of those neuromorphic computing elements. On the sensor part, we're going to focus on the event-based camera, and on the processing part, on the spiking neural networks. What is an event-based camera? Instead of recording information as frames, like a normal traditional camera would, the event camera will record information at each pixel asynchronously by recording events, so activations, only if there is a change in the luminosity. If the luminosity decreases, then we have negative event, and if it increases, we have positive events. So here on the right, you have an example of a real-life scene as recorded by an event-based camera. And this kind of data that we call event data produced by these cameras are really interesting for three reasons. First of all, it requires really low memory to be stored. It requires also really low energy to be recorded by the camera. And finally, it makes a really, really good match with spiking neural networks. Spiking neural networks, what is it? It is inspired by the biological neuron that understands information and transmits this information as electric activations that we call spikes. And this electric activation, we managed to re-implement those on computer. And they are taken, so they are given to a spiky neuron with different amount of influence depending on the weight of the synapse. This electric activation will increase the membrane potential until the membrane potential reaches a certain threshold. And once the threshold is reached, then you have spikes that are output by the spiking neuron. And this kind of artificial neural network that is really bio-inspired can be implemented on specific hardware called neuromorphic hardware with a really low energy consumption. So first of all, the spikes can be simulated using either CPU or GPU simulators that can be either clock-driven or event-driven. And in terms of hardware, we have digital or analog hardwares within which we can mention the FPGAs and the ASICs. And the most famous one that we can mention here are the brain scales, the Spinnaker, the Neurogrid, the True North, and the LOI, and more recently, the academic platform Kraken. During my PhD, I'm going to present to you some results that we obtained on 4 of those neuromorphic targets. On the CPU simulators Nest interface with Spine, and on the neuromorphic hardwares Spinnaker, LOI, and the academic platform Kraken. As I told you earlier, the spiking neural networks applied to event-based data make a really, really good combination, so they make a good match. And with those two combined, we can achieve many computer vision tasks. So in this presentation, I'm going to show you results with specific computer vision tasks that are the localization, so saying, okay, in an image, where is the object of interest? The classification, so it is giving label to this object. And for the classification part, we are going to present results obtained with 3 benchmark classifiers. The first one being the one implemented using the Slayer framework introduced by Shrestha in 2018. The second one using the PELIF neuron model that was introduced by Fang and colleagues in 2021. And the final one is a classifier extended from odds by our colleagues Grimaldi and colleagues in 2023. And the final task that we're going to present results of during this presentation is the semantic segmentation, which corresponds to giving a label to each pixel in the visual scene. As a result, we are going to obtain were obtained with the FSegnet model introduced in 2019 by Alonso. And we're going to apply all those different computer vision tasks to different event-based datasets, such as the private IMRA pedestrian dataset that were provided to us by our collaborators at IMRA to achieve localization. For the classification, we are going to use the DVS 128 GST dataset introduced in 2017 by Amir, and the neuromorphic NNIST dataset introduced by Orchard in 2015. And finally, for the semantic segmentation, we are going to use the Davis driving dataset 2017 introduced by Vinas in 2017. During this PhD, we had a main core research problem, which was how can we optimize the trade-off between quantity and quality of the visual information as a preprocess for any embedded data processing? In other words, we want to be able to process the event data while keeping the similar amount of relevant information in the data while reducing the number of events in order to achieve a reduced energy consumption. But I told you earlier that the event data is quite light and does not require a lot of energy. So why should we actually reduce the size of event data? Well, if you take a look at most recent data sets that were recorded, for example, the Prophecy 1 megapixel automotive detection, you can see that the bigger the sensor, the more events you record. So for example, here, you don't have a lot of information on the details because there are too many events, it began to be a bit saturated. And this is especially the case for very dynamic and textured scenes that record up to several million events per second. And we it is really highly doubtful that there exist embedded systems currently that are able to understand, to process that many events at the same time. The embedded system, if they process that many events, they will not keep everything, they will drop some of them. So what we want to do, we want to be able to decide which events we want to keep and which event we want to lose in order to only keep relevant information for the computer vision task that we're going to achieve. So to answer to this main core research problem, we implemented 3 main contributions that I'm going to present to you now. The first one is event data downscaling. The second one is visual attention. And the third one is neuromorphic foliation. So we're going to begin with the first contribution, event data downscaling. Before the beginning of my PhD, to the best of our knowledge, there existed only one method to reduce spatially the event data. It was implemented by the Tonic framework in 2021. And what it did is that it took region in the input sensor, reduced it to 1 pixel. And if there was an activation in the region, then you will have an activation always. So this will lead to data that the smaller it gets in dimension, the more saturated it gets. So let's just look at an example to see what I mean. If we take an original sample of 138 by 128 and we reduce it by 5 using this method, you can already see that you have a higher activation rate and you kind of lose the details. And when you don't scale it by 10, you don't understand anything anymore that is going on. And if we compare that with RGB video of the same dimensions, we can see that reduced by 5, you can have still interesting information, and reduced by 10, you can still kind of understand better than for the event data. For the RGB video, there exists a lot of different downscaling methods, and so we believe that it was really interesting to implement and to study the subject for event video. In order to implement those different event data downscaling, we adopted 2 different strategies during this PhD. The first one was to do some spatial downscaling. So we kept the same temporal resolution and we reduced the spatial resolutions. We reduced the length and the width. And to do this spatial downscaling, we implemented 6 different methods during this PhD. The first 4 are the spatial funneling, which is a re-implementation and adaptation of the Tonic method that I told you about earlier. There is also the event count and the linear and cubic log luminance reconstruction. And those 4 first methods were introduced in our paper at VISA 2022 with the help of our collaborators at IMS. We also implemented 2 additional methods using this time neuromorphic processing, so spiking neural network pooling that considered the events, the polarity of the events either as separate or with a mutual influence. And those 2 methods were introduced in our paper at WACV 2023 with the help of our collaborators at IMSC also. We wanted to compare the quality of those different methods of reductions because in our goal, we want to reduce the number of events but keep a similar or as close as possible accuracy in the information. So what we did is that we classified the reduced dataset using the cell layer classifier for both the neuromorphic MNIST and the diverse 128 gesture dataset. And we tried to assess which method was the most interesting one. So for the spatial funneling, as you can see, we have an accuracy that seems to be well maintained, but the issue is you don't lose many events, you really use just a few. And this is not our goal at all. We want to reduce this number of events as much as possible. So here with those results, we believe that is the separate or mutual SNN pooling seems to be the most interesting one because you lose a lot of events, but you keep a high accuracy. We then adopted a second strategy in order to reduce those event data, which is temporal downscaling. So we keep the same spatial dimension and you reduce the temporal dimension. And to do so, we implemented 4 different methods this time. We implemented the temporal synchronous and asynchronous funneling, as well as a deterministic and stochastic structural downscaling methods. And those 4 methods we introduced in our paper at the event-based vision workshop at CVPR 2023. And this time we also compared those different methods together. And we took a look at the evolution of the accuracy performance using the PLIF-based classifier. And we can see here that those methods seem to keep a really, really high accuracy in terms of classification, even with a really high reduction. So, but this can be explained by the fact that the PLIF-based classifier accumulates events into frames. So if you have grayscale frames with more or less events, you still have some information. So we want to extend this comparison between those different methods and with the spatial ones with an additional evaluator. And this additional evaluator was the first ever human assessment study performed on event data. What we did is that we asked some volunteers to classify between different samples from the DVS 120 gesture datasets that were downscaled at different level of resolution with the different methods. And we asked them to recognize which motion it was in order to really see what does human being understand from this reduced data. And these results were introduced in also in our paper at Event-Based Vision Workshop of CBR 2023. So here we have those results, and we have 3 interesting things to see on those results. So first of all, those results also help us to determine the dividing factor for each method above which the human does not understand what is going on anymore. Also, the second thing that can be really interesting is that if you compare here between the spatial dividing factor, you can see that the spatial funneling, the event counts, the linear and cubic, spatial funneling, event count, and both SNN pooling methods all have the same accuracy from a human point of view. And we also know from results that were obtained before that the amount of events are really more interestingly downscaled with the SNN methods. So this seems to confirm that the result that we obtained earlier. And finally, these results provide us with really interesting insights on the way human beings understand event data, because we can see, especially for the temporal reduction methods, that the human beings do not understand the same things than the machine at all. So the machine had higher results for a longer time than the human beings. So let's sum up this first contribution on event data downscaling. During this PhD, we implemented 10 different methods that were either spatial or temporal to implement event data downscaling. And this led to a high variation in the optimization of our trade-off between quantity and quality of the event data. And those results showed us that this strongly depends on the chosen method, the dividing factor, and the application task. Also, our original human performance assessment experiments led us to interesting insights into the human perception of gesture classification using event data. Let's now go to our second contribution on visual attention. So we saw before that we managed to have interesting results in the optimization of our trade-off, but we did not reduce the data while looking at things that were interesting in this data. So this is what we're going to do now. We're going to apply visual attention to keep all the interesting things and not globally. So what we did, we implemented first a model of saliency detector using spiking neural network. So this is a really simple model with only 2 spiking neural network layers. We have the input layer that is connected to the saliency detector layers with a downscale excitation, which is kind of a convolution with no overlay. Then the saliency detector is submitted to a soft exponential winner-takes-all, which is a way to do some clustering in a bio-inspired way. And this way we have the activation in saliency detector that are really clustered together, and we can have really specific localization in the sensor of different objects of interest. And finally, we added a weight adaptation rule that says that if there is activation in the input layer, then the corresponding region saliency detector will see the activation be stronger with an increasing of the weight. Because if there was something interesting recently in this region, then it is most likely that it is going to keep on being interesting, and vice versa. If there was no activation, then we're going to decrease the weight. From this saliency detector, we implemented a spatio-temporal filtering model that detects objects of interest in the event data one at a time. So what we did here is that we added one output layer to this first model that is connected to the input layers with a one-to-one connection. also submitted this, to an exponential winner-takes-all mechanism, and we added a threshold adaptation rule. So this threshold adaptation rule, what it does is that it decreases the threshold in the region that were considered as interesting by the saliency detector. So regions where there were some activations in the saliency detector in order to facilitate the activation of these regions. And if there was no activation in the saliency detector, then we increase the threshold to hinder the activation and to only let through events that correspond to things that are interesting according to our saliency detector. And this first model of spatio-temporal filtering was introduced in our paper at ICAS 2022 with the help of our collaborators at ETH Zurich. This first model, we wanted to validate it to really see, okay, what does it consider as interesting in our event data? So what we did is that we took different samples from the DVS 128 gesture dataset and put them side to side with a time shift between 0 to 500 microseconds in order to understand what was considered interesting. Was it the number of events? Was it the activation rate? Was it the maybe the time the object of interest appeared first in the sensor? And what we saw with this result that first of all, we do manage to obtain only one object of interest in the output layer at a time. And we also see that the output object of interest has an activation surface that is 0.1% of the original surface. And this is confirmed by the fact that the size of the object of interest is equivalent to the 20% of the original size in terms of width and height. So we see here that the in our trade-offs, the quantity part is achieved, so we managed to reduce the activation of our sensor. But do we manage to keep a good quality in this object of interest that is output by our model? Well, the third panel here seems to show that yes, because the classification accuracy obtained on this object of interest corresponds to 73% of the original classification accuracy. So this is interesting for us. We also validated this task on a localization task. So this model was applied to the IMRA pedestrian dataset. When we compare this model to the state of the art, we can see that this model has a precision and a recall in terms of localization that is similar to the state of the art. But when we add noise in the input data, this model achieves a precision and recall that is better over the long time, over the increase of noise in the data, better than the state of the art. And those results were introduced in a paper that we co-authored with IMRA and that was published recently in July 2023 at MBA. We also wanted to validate this model on neuromorphic hardware. So what we did is that we implemented this model first on low-E without the weight and threshold adaptation rules, because low-E do not allow for the implementation, for the modification of upper parameters during the runtime. And we also assessed the implementation on Kraken. And here with those results, we can see different really interesting things. So first of all, the implementation on neuromorphic hardware seems to be really interesting in terms of simulation time. So for the decision latency, it's a bit smaller than with the CPU implementation, but still interesting enough. And when we look at the classification accuracy, it seems to really show that Kraken is a really interesting alternative to implementing SNN than the CPU simulators, for example. And those different results were introduced in our paper at ICAS 2023, also with the help of our collaborators at ETH Zurich. Finally, we also wanted to validate this model on the neuromorphic hardware Spinnaker. So we assessed the energy consumption on Spinnaker. So if we just take a look at the number of neurons and number of synapses, it seems that our model has a fewer amount of neurons, but a bigger amount of synapses. And it was interesting to see how this translates into energy consumption. So this result shows us that for the initialization part, our model takes more energy, consumes more energy than the state of the art, but during the runtime, it consumes less energy. So this is quite promising for this model and for the implementation on neuromorphic hardware in general. And these results were also presented in the paper we co-authored with IMRA at MBA 2023. Now that we've finished validating this first model, we also implemented a second model for multi-spatio-temporal filtering. So now, instead of detecting only one object of interest at a time, we are going to detect multiple objects of interest at the same time. So in this example, I have only 2 output layers, so 2 objects of interest can be detected at most simultaneously. But theoretically, we could increase this number of output layers and possible object of interest to an embedded number, with the only downside that this increases the number of neurons to simulate. So what we did here is that instead of having 1 output layer, we put 2 output layers, also connected in one-to-one to the input layer, also submitted to an exponential winner-takes-all mechanisms. And this time we have a threshold adaptation rule that is updated. Instead of taking into account only the activity in the saliency detector, we are also going to take into account the activity in the lateral layers in order to let through only 1 object of interest per output layer. And this model was introduced first in an oral presentation at GDR Vision 2023, and also via an oral presentation at Oasis 2023, and finally in the conference proceedings of IGCNN 2023 with the help of our collaborators at ETH. We wanted to validate this model experimentally, so you can see here with this example that we do manage to obtain 2 objects of interest that are simultaneously detected in 2 separate output layers. And this is confirmed by source results. So on the panel on the top, you can see that this performance of simultaneous detection, so 2 objects of interest in 2 different output layers, is actually correct at most 50% of this time, but we believe that this could be better in the future with a further hyperparameterization phase. And this is also quite promising in any case, because if you look at the classification accuracy of the output object of interest, it is really quite close to the original classification accuracy. So we do manage to keep a good quality of this output object of interest. Finally, we compared our 2 neuromorphic models to the state-of-the-art, so the models of saliency detection introduced in Renner and colleagues 2019 and by D'Angelo and colleagues in 2022. We can see that if we compare between the number of layers and number of neurons, our model is better or similar to the best state-of-the-art. And in terms of synapses, we are in the average. But what is specifically interesting is that these 2 models are able to do some additional functions that the state-of-the-art cannot do. All of that with a detection latency that is better than state-of-the-art. To sum up the second contribution on visual attention, we are able to implement 2 model of neuromorphic model. Implement a neuromorphic model for visual attention, selecting either 1 or multiple objects of interest at the same time. We implemented those on CPU, Lowy, Spinnaker, and Kraken. And those models led to the reduction of event spatial repartition to 20% of the original repartition, and while maintaining a classification performance of 70% of the original classification. All of this with a detection latency of 15 microseconds at most. And finally, the simultaneous salience detection is effective at most 50% of the time, but still shows really promising results for the future in this specific research field. So now that we have spoken about event data on scanning and visual attention, we want to introduce the concept of neuromorphic foveation. Foveation is a biological concept where the human eyes detect more details where the gaze is directed than in the periphery of the vision. And this concept of neuromorphic foveation was actually introduced by our collaborators in IMSC, so Teresa Celano-Cotalidana, in 2022. Through the concept of a foveated event camera hardware. However, with COVID issues, this hardware did not exist during my PhD, but we were still convinced that this concept was really interesting, because we believe that thanks to neuromorphic foveation, we will be able to reduce the amount of raw data to handle while preserving most of the relevant information with a significant energy efficiency. So really doing the answering our core research problem. And so what we did, we implemented this neuromorphic foveation not on hardware, but on software. And this concept of software neuromorphic foveation was introduced in a poster at Oasis 2021 and GDR Vision 2021 with the help of our collaborators at IMSC. To actually implement this software neuromorphic foveation, what we did is that we implemented in a binary way. We took event data at high resolution and reduced it to low resolution. On this low resolution, we detected the semantic, so the region of interest, what was interesting in this low resolution. And with the localization of region of interest, high resolution and low resolution event data, we performed some multi-resolution merging in order to obtain a foveated dataset. And this binary neuromorphic foveation concept was introduced in a poster at the Neurovision CVPR workshop in 2022 with the help of our collaborators at IMSC, and this poster actually received the Best Poster Award. Finally, we wanted to validate this binary neuromorphic foveation on software, and we did so on 2 computer vision tasks. First, on the classification using the odds algorithm introduced by our colleagues at INT, and then the semantic segmentation using the FSegnet model. And this result that I'm going to show you now were all published very recently in the journal paper in biological cybernetics in September 2023. And all those results were obtained with the help of our colleagues at IMSC, but also at INT. So first, we validate this on classification. So here you have an example of a sample from DBS 128 gesture that we reduced and to which we applied also visual attention and neuromorphic foveation. You can already see that the number of events is reduced compared to the original one. And when you compare this with the classification accuracy of odds, you can see that the foveated data here in red seems to have a classification accuracy that is really close to the original one, at least way more interesting than the one obtained with low resolution or visual attention, while keeping only half of the original events. So this is quite promising, and those results were confirmed when we apply semantic segmentation. So here we do the same thing as before with the classification. We applied event reduction, visual attention, and neuromorphic foveation on samples from the Davis driving dataset 2017. And we can also see here that the number of events is more interesting than the one in the original data. And when we just take a look at the semantic segmentation results, so the accuracy and the MIOU of these different samples, you can already see that the foveated data have an accuracy and an MIOU that is really close to the original and significantly better than the one obtained with the 2 other methods. And this is confirmed with when you take a look at the whole data sets. You can see here that we managed to keep only 1/3 of the original events, but still keep a performance that is not significantly degraded, really close to the one of the original events, original dataset. And something really interesting with this neuromorphic foveation on semantic segmentation, we can see that here, when we take our dataset, we reduce it, apply to visual attention or neuromorphic foveation, and then from that, we stochastically select a smaller percentage of events, and we apply to that semantic segmentation. We can see that the foveation seems to keep an accuracy that decreases not as much as the original one, and that stays better than the one obtained with visual attention or reduction. And this accuracy seems to come even really close to the original one. And this specific observation can be explained by the fact that in the foveated data, you have a higher percentage of interesting events and a lower percentage of non-interesting events than in the original dataset. So to sum up this third and final contribution on neuromorphic foveation, we managed to implement a software version of this concept, and that showed us that it could bring significant benefits for optimizing the trade-off between event data quantity and quality. And specifically for semantic segmentation, you can see that we maintain a similar performance while decreasing the number of events by 2/3. So now I'm finished showing you our main 3 contributions for our main research problem. But during my PhD, I also took a look at other research problems, and we can specifically look at specific results that can be bring together with this second research problem. That is, how can we exploit the relevance of the spiking neural network to process a specific chronology of event data. I told you that the event data and the SNN make a really good match, especially in terms of temporal information, because the event data has a time grain that is really small, to the microsecond. And we believe that those two combined can be really interesting for specific application tasks where we need to focus on temporal information at a really low grain. So let's take a look at our 3 application tasks that we took a look at during my PhD. So the first one is coastline detection. This first task was, we choose this first task, first of all, because it is a use case of the Aprovis 3D project, so within which I'm doing my PhD. And we believe that it would be interesting to process this with SNN event data combined. To process this first application task, we adopted 3 different strategies, including delay learning. So in artificial neural networks, traditionally, when we do some learning, we update the weights according to the activity in the network. But with delay learning, what we do is that we update the delay, so the time it takes for one spike to go from one spiky neuron to the other. And to actually work on this delay learning, we first did a bibliographic synthesis of both biological and neuromorphic delay learning. And also we re-implemented the model introduced in Adaptation 2018 and worked on it in order to, in the future, apply it to real-life data. And those, this contribution led to the 2 publications, one in the journal Brain Science 2022 and one in JOBIM 2022. And it was done through the supervision of 9 internships. Another strategy that we adopted for the coastline detection was the sea-ground segmentation, and this is currently something we're working with in an Aprovis 3D work group, reuniting NTUA, INT, and us at UCL. Our second application task is 3D reconstruction. So this is a secondary use case of the Aprovis 3D project. So this is why we also took some interest in that. And what we managed to achieve for this 3D reconstruction task, it was the adaptation of the cooperative stereo matching model introduced in 2017 by Likov, and that originally ran on 6 spin-5 boards, and we managed to adapt it to run on only 1 spin-3 board by updating the architecture of the network and also working on the reduction of the input data. And this was done through the supervision of 2 internships. And finally, our final task is the lip reading. So we believe that this is a really interesting use case for the specific chronology of event data, because to read on lips, you need to have a precise information according to time. And in this PhD, we implemented the first end-to-end neuromorphic lip reading model. And this was done through the supervision of 4 internships that led to the recording of 1 dataset and to 1 publication in the event-based vision workshop at CVPR 2023. So to conclude on these presentations, I told you about all the results that we obtained for this first core research problem of how can we optimize the trade-off between quantity and quality of the visual information as a preprocess for any embedded data processing. So first we implemented event data scaling with 10 different spatial or temporal methods that lead to a trade-off optimization. And we saw that it strongly depends on the chosen method, the dividing factor, and the application task. We also implemented a neuromorphic model for visual attention that selected only 1 or multiple objects of interest at the same time. And this led to the reduction of event spatial repartition to 20% of the original one, and while maintaining classification performance of 70% of the original one. And finally, we also implemented on software the neuromorphic foveation concept, and that led to significant benefits for trade-off optimizations. And we managed to keep a similar performance of semantic segmentation while keeping only 1/3 of the original events. We also took a look at a second research problem that was how can we exploit the relevance of spiking neural network to process the specific chronology of event data, while taking a specific look at 3 applications, the coastline detection, so 3D reconstruction, and the lip reading. And all in all, we believe in the usefulness of neuromorphic computing for the future of AI, thanks to its low memory and energy consumption, as well as its high adaptability. Following this PhD, we have some perspectives. So in terms of scientific work, in the short term, we believe that it would be really interesting to do a benchmark for the results that were obtained between frame-based and event-based video, as well as between standard artificial neural networks and spiking neural networks. In the medium term, we would really like to apply our delay learning model to real-life data in order to detect spatiotemporal patterns in the sea and the ground and then segregate them. And finally, on the long term, we would like to validate on hardware the neuromorphic foveation concept, because our colleagues at IMSC finally received the electronic foveated event-based camera. So outside of my research, my specific research, the model I worked on for visual attention will be continued to be developed in the CIFRE PhD with an application to autonomous driving with the help of our colleagues at IMRA. And this CIFRE PhD is one of Mr. Hugo Bulzemi that will start next month. There is also an ANR-funded French project called NAMED that will work on neuromorphic bottom-up and top-down attention models for event data, and we start in February 2024. And finally, for my part, I will be doing a postdoc that I will start in December, next December, within the Green AI project at the IMS lab in Bordeaux. And I will be doing edge computing and neuromorphic captors fusion, all of that still with the common goal with my PhD of doing some low energy artificial intelligence. So here in this final slide, we have all a recap of my presentations. So all those results were implemented thanks to the our collaborations with INT, IMRA, and specifically ETH Zurich and IMSC, where I did 2 one-month stays, and all my results were published within 2 journal articles, 9 conference papers, 4 extended abstracts. Thank you very much for all your attention, and I am ready to take your questions.
Thanks. In time, so we'll it's now time for the questions, starting by the reviewers, but I would like just to check if Riyad is connected to the
I don't know if I can show you both the reviewers and the... Okay.
No.
Yeah.
So it's not yet for the moment. So we will start with the question of the reviewers, the 3 reviewers, and in the following order, we will start with Chiara Bartolozzi from IIT, then Timothée Masquelier from Serco, and finally with Michel Bandavoine from LEAD here in the room, and then we will go to the have the questions from the members, the examiners of the jury. So Chiara, you can start your question, and I would like to give you a word about my role as timekeeper, and so to take into account the time constraints of the member of the jury here in the room, traveling constraints, and so I will ask you to take no more than 15 minutes for your questions. Okay, so that means that we have something like 2 hours. All of us all together for the questions. Okay, so Chiara, you can start.
Hi, thanks a lot. Thanks for the instructions. Just kill me once I hit the time limit because I don't have a watch. So thanks a lot for the presentation. It was very clear and interesting. And as I wrote you already, I think your work is timely and useful to the community. So of course I have thousands of questions. I try to concentrate on the ones that I think could be more important. So I understand that you first explored the idea of data reduction for going towards embedded systems and lower power, lower latency, and so on. But you presented kind of 2 very different scenarios in a way. The data reduction in the second part, that is based on visual attention, seems to be kind of useful in tasks where you have an object and you need to do recognition, or at least you need to process a regional interest in the data. But the application in the coastline detection doesn't seem to match this work on the visual attention. So I imagine that for that task, if you want to do some data reduction, you cannot use the visual attention method, but you need to resort to one of the first ones. So I wanted, some comments about this on, the applicability of the different methods of data reduction. Which one would you choose for which type of task? Kind of a more recent discussion about this.
Yeah, you are totally right. It totally depends on the application task, on which method you would like to use. So yeah, for cosine detection, for example, you should either choose one of the event data downscaling methods, or maybe the foveation part, because we said that on semantic segmentation, it was really interesting as well. It provided really interesting results. But during this PhD, we also wanted to not specifically take a look at the cosine detection task, but also like more generally, how can we bring this trade-off between quantity and quality to like any computer vision task. And it would be really interesting to. So here we focused on localization, classification, and semantic segmentation. But I believe that applied to like any other things that would be also really interesting to compare together what we would obtain. Yeah.
Okay, so and still about this downscaling of information. In the first part of your work, you clearly separated the spatial downsampling from the temporal downsampling. Do you think there's a way to combine the two that could, improve on certain aspects? Can you discuss about this?
Yeah, actually, it was one of the perspectives that we introduced in the manuscripts, but not here in the presentation. We believe it would be really interesting to compare what we would obtain if we separate them or put them together. And already one of the results that we presented today, I'm going to just share the screen once again to show you which one I'm talking about. Kind of already combines those two together, but we did not say it as such. This result here, when we took a stochastic percentage of the data sets, we perform actually the stochastic structural methods that we implemented. And we applied that to some low resolution data. So actually here we did combine spatial and temporal downscaling. We did not have the time to really compare more specifically the results it brings compared to those two separately, but it is possible because we already did it once. Yeah.
Okay. Then if you talking instead about the visual attention part. So I guess you have this this way of selecting multiple region of interest, yeah, using different output maps, let's say, that, right, if I understood correctly, you have this sort of saliency map, and then you have different ones where you only select the region that selects one specific object, and you can have multiple of these, right? So in this way, you have simultaneous selection of multiple regions at the same time, using. So I guess then you would feed each of these maps to a different, I don't know, recognition network or whatever to do the processing. So there are, in this case, the crucial thing is being simultaneous, right? And you use resources, and you basically duplicate the computational resources that you need to represent each single object.
Yeah.
Right? Was there a need to have this simultaneous? Or could you think about other methods like a temporal selection in a sequence that selects different objects one after the other? Why this choice?
So this is a really interesting question. Thank you. So we began working on simultaneous selection of multiple objects of interest through discussing with our collaborators at ETH, so Michele Magno. because we believe that for embedded system, it would be really interesting to not focus on only one object of interest, but multiple at the same time, because in real life environment, you have a lot of details coming in at once, and it should be really interesting to focus on all of them at once. But this model, this architecture that currently exists, has the downside here of increasing the number of neurons, so the energy consumption. And so during this PhD, and we did not have the time to really develop that as much as we wanted to, but we were beginning to work on a way to have like an adaptive network that would simultaneously select and then autonomously reduce the number of neurons when there was no activated object of interest, nothing interesting going on, in order to really reduce as much as possible the energy consumption. And we also took an interest, let's say, to like the saccade work. So like try to mimic what the human eyes does, because the human eyes can only detect one region of interest at a time. That's actually the foveation. We have only one fovea, so we can only detect one region of interest at a time, one object of interest. But we're able to do that really quickly, and then saccadically, we have the eye that moves and goes to another one, and so on, and so on. So that would be the temporal part that you suggested, like having one object of interest and another one and so on really quickly. And this would be also really interesting, but we did not have the time to pursue this direction. But yeah, it would be really promising as well to take a look at this, especially when we know that we have decision latency that is quite quick with our model.
Okay, cool. Yeah, so you trade off somehow your resources with the behavior. So if I have time, I have another couple of questions with respect to the hardware implementation. Yes. I have two actually. One is, so you mentioned that you took your networks and you implemented them on Loihi and Kraken. So the question is, because of my ignorance, I don't know Kraken. So can you just give me an idea of what it is and why it's different? How is it different from other neuromorphic platforms, especially Loihi? That's the one that you use.
Yeah. So Kraken is an academic platform that was developed by our collaborators at ETH Zurich, specifically by Alfio Di Moro, that is currently in postdoc. And so since we worked with him and developed this hardware that is able to run both artificial neural networks, but also have SNE to specifically implement spiking neural networks on this, we thought it would be really interesting to assess the quality of this board with an existing model and to compare it with the implementation, for example, on Loihi, which is like the state of the art in terms of hardware, neuromorphic hardware. And it is different. I wouldn't really be able to tell you all the microelectronic details, but yeah, it's not exactly the same behavior in terms of.
Okay, and so when the models that you showed when you kind of compared yours, the one by Alpha and the one by Julia, in terms of different resources, you compared the power or the number of computation steps and the neuron and synaptic resources that you need to implement the networks. And there's a clear difference between the models in terms of number of neurons and number of synaptic connections. Now, when you plug that into a neuromorphic hardware, most of the times the real limitation is in the number of synapses. Did you hit that limit? Did you have problems in mapping the network onto the resources available on a hardware?
That's a really interesting question. What we did is, so we assessed the implementation on Loihi, on Kraken, and on Spinnaker. And on Spinnaker specifically, we know that it is quite reduced in number of neurons and synapses that we can implement. So we produced some results where we reduced the input data in order to be able to fit in on the hardware. But in terms of number of synapses, this was really the number of neurons that limited us in the implementation. specifically for Spinnaker, but also for Kraken, if I remember well. And the synapses was less of an issue in this model.
Okay. So to me, I'm kind of fine. I might pop out other questions and stay for 1 hour, but maybe it's time to move to the next. Thanks a lot, Amélie.
Thanks, Chiara. So now it's time for Timothée.
Okay. Okay, well, first I wanted to congratulate you, Amélie, because the amount of work you've done is impressive. The topic is very timely because the current AI technology consumes way too much. We all agree on that. You've been very productive. You have many papers. Also, something that is very impressive. It's a very interdisciplinary work. Sorry, and you did both some software and some hardware, and this is not common. I know that you did the hardware with some collaborations, not alone, but still it's very impressive. Many people stay on the software side and say stupid things. So I think it's good to go until the implementation. Okay, after that, of course, I have some mean questions for you. Now, the first one, I think you mentioned that in the next steps, so I'm happy about that. But for me, it's a suggestion would be to do a more rigorous comparison between SNN, DVS plus SNN on one side, and standard camera plus ANN on the other side. And so you mentioned that in your next step slide, so I'm happy. But can you tell me more about that? How do you plan to do it? Why didn't you do it before?
Yeah. Okay. But first of all, thank you very much for your first part of your comments. And secondly, so for this part, if I had another year of PhD, I would have done it. That's true. But so why did I not do it? Sadly, because I did not have the time to really do a specific, really intensive comparison between those different things. But I do believe that it is interesting because here I'm telling you in the beginning that artificial neural networks consume a lot, but I don't have clear comparison. But with all the approximations that we did and all the estimation that we did, it seems to still be to our side. And how I would like to do that. So first of all, I would like to, for example, on event-based event data downscaling method, visual attention, and foveation. So we like to compare the result that we would get when we use the SNN classifier versus the ANN classifier on those different type of data. That would be really interesting to see how it actually evolves. Does the SNN are better in terms of accuracy, in terms of energy consumption, and do we have the same results, especially when we take a look at the different methods that we implemented? And for the event versus frames, that would be the similar kind of comparison, but this time taking a look at, for example, our visual attention model that is implemented with SNN, trying to see, okay, do we manage to do the same things with both? Is it really more interesting? Does it take less times, etc., etc.? But this will be also quite a step to really take a look at how can we translate RGB data into spikes, but I think that's like common research problem that is going on.
Yeah, there are solutions for that.
Yeah.
So my recommendation would be really to do a rigorous comparison on the same task, and you can either compare energy consumption at ISO accuracy, so you make the two systems with the same level of accuracy on the same task, and you compare the energy, or you do the opposite. You do the same energy consumption and you compare the accuracy, but because otherwise you cannot conclude anything. And unfortunately, I haven't seen a very convincing paper doing that in the literature yet. And I think you could do it, right? Because you have all the skills. And also, one of my recommendations would be, not to be careful in the ANN you choose, because this ANN community is making a lot of progress as well in terms of energy consumption, right? And they have invented very fancy stuff like quantized ANNs, and don't use don't use off-the-shelf GPU. Use a low-power one, NVIDIA Jetson or similar. I mean, because and if you do that, it's not clear who is going to win, and I think it will depend on the task. And I don't think gesture recognition is a good task for that, because in fact you don't really need a fine temporal resolution to do gesture recognition. So you lose one of the advantage of the DVS and SNN.
Yeah.
Okay. Okay, that was my first question. Second question. You know, before the deep learning revolution, people would design some, would extract some features manually from the images or from the input, and then use a classifier like a support vector machine or anything to do the. For instance, if I'm going to focus on classification problems just for illustration, and then the deep learning revolution came. And in the deep learning community, people don't do that anymore. Right? The idea is more to feed the raw data to the network, to do as little pre-processing as possible, because you let and to do some end-to-end training, and then you let the network learn what is useful to do the task. And you don't do that, right? Most of your contributions, you insert something between the sensor and the network that does the classification. You insert some pre-processing, and this involves a lot of, you know, arbitrary choices or parameter tunings that you have to do manually. So basically, you're a little bit swimming against the tide. And can you comment on that? Why?
Yes. Okay. I can go on. So this, what we try to do. So indeed, we put like this intermediary steps between the recording of the data and putting it in the network.
Yes.
But in the further contributions that we did, specifically the visual attention part and the foveation, we wanted to implement networks that would not have to be specifically tuned to a specific task or a specific data set. We wanted to have something that is really adaptative, especially in order to not have the issue of doing some previous hyperparameterization, like you just said, like to try to remove this issue here. And that is specifically why we implemented weight adaptation rules and threshold adaptation rules. But this is really something we had in mind because we wanted to have this to be the most general possible, the more adaptable possible.
Okay, but don't you think, okay, it's the problem with generic, I get your point. It's generic, which is good for you because you do the tuning manually, you don't want to do it for each, you know, problem you want to solve. But, you know, genericity is often suboptimal, right? And the beauty of backprop, in my opinion, it will, you know, optimize all the steps, including the pre-processing steps for the particular task you want to solve. But so it's specific, but it's not. It does not involve manual tuning. You know.
Yeah.
One illustration of that is, for instance, so in chapter 6, where you want to reduce the spatial and temporal resolution of the DVS output. So, one of the solutions you propose is SNN pooling, right? You add an SNN layer which will reduce the resolution. But then and that works nicely, okay. Well, but then if then you give this output to a SNN classifier, why don't you have one integrated network and train it end to end with backprop? Yeah.
Sorry. So this is like one direction that we decided to take in this PhD because we wanted to first demonstrate that it was possible to do this downscaling with SNN. But what you propose is really a good idea also as well, a good concept, but and that we just did not take the time to implement. Yeah, and we will. Yeah.
Okay, so it's an idea for your postdoc.
Exactly. Yeah.
Yeah, so if I stay on chapter 6, so the methods to reduce spatial and temporal resolution, it took me a while to understand that what you really want to do is to reduce the number of events, right? More than the spatial or temporal resolution. And can you comment on that? Why do you think reducing the number of events is so important? Is it always true? I mean, does it depend on the downstream system or?
So thank you for this question, because I have some interesting data to show you into this. Let me just go to see. Oh, it's like, so I did some research that is, sorry, not complete. So to take a look at the final column. But yeah, we did some research to really assess is the number of events important in terms of the energy consumption? We wanted to see, okay, is our core research program really like correct in terms of scientifically? And we saw that, yeah, indeed, for each main neuromorphic hardware that exists, the energy consumption of the hardware really depends on the synaptic operations. So actually on the events that are taken into account by the network, and then all the spikes that come from that then comes into the network. So we believe that, yes, one really interesting thing to reduce the energy consumption is reducing the number of events. But as you actually did tell in your feedback, and which was really interesting, thank you for your feedback, by the way, we know that depending on if the hardware is clock driven or event driven, this number of events will have more or less of an impact. It will still have an impact, because as we can see, it does create energy consumption specifically by events. But if we specifically, for example, did some temporal downscaling on clock-driven hardware, then it is more interesting to actually do the temporal downscaling than specifically reducing the number of events. And we thought that was really interesting to start, like, to go as general as possible and do this reduction of events, of number of events as it is. But it was also interesting for us, depending on the application cases, to do some spatial or temporal reduction and really like separate those two strategies and try to, depending on the application task that we have.
Okay. Yeah. Okay. This table is quite convincing indeed. I do believe that on most neuromorphic chips, the energy consumption is really related to the number of events. That being said, with your methods, you only reduce the number of input events, right? And if you feed them to a very deep SNN, then it's not clear that you reduce the number of input events, but it does not necessarily imply that you reduce the number of events in the subsequent layers. So maybe it's the total impact on the whole energy consumption is maybe not that strong. What do you think?
We took the original hypothesis at a spiking neural network. Like, if you want to do some bioinspiration, you don't have a lot of layers. So we were really focusing on spiking neural networks, small spiking neural networks, let's say, and we did not really take a look at the deep ones. But in any case, we also believe that, except if you do like activation, self-activation of further layers down the network, normally the activity really depends on the input activity.
Yeah, it does, but it can be controlled. I mean, if you train your network, you can, for instance, encourage sparse activity inside. So, okay. Also, there is one solution that you did not explore. So basically you try to reduce the number of events and you kept them as binary, like all or none events. But there is also another solution, which would be to use, for instance, to use spike counts over certain, delta t, and to transmit, to use graded spikes or graded events to transmit those spike counts. And I understand that each of these events would, take a little bit of more memory and maybe would be a little more, will consume more energy to process, because you have a multiplication to do, not only an addition and so on. But still, it's a trade-off, right? Because you could have fewer events. Each event cost a bit more, and this trade-off should be explored, no?
Yeah, it is another path we could have taken, as you said, and it's quite interesting. But yeah, during this PhD, we really wanted to focus on events per se, like keeping the same format, structure of events, and not do some, not modify them into spike counts or anything else. But this would have been really interesting as well. I think there are some studies that exist on event data compression and modification in the other formats. Yeah.
Okay. I'm looking at the
your time is over. Yeah, your time is over, Timothée.
My time is over? Okay. So no more questions.
Sorry. Sorry for that. And so now leave the floor to Michel as the third reviewer.
Thank you, Mr. President. Okay, so first of all, I would like to congratulate you about your presentation. It was a very nice and didactic presentation. So it's first very positive comment, okay? And that is in the continuity of the reading that I had about the manuscript. It was very nice, and a lot of information inside, okay? But it's very compatible with a lot of work that you did during your PhD. Again, second congratulations about that, because I am very impressive about that. Okay, so as you mentioned, so you did you proposed 10 different algorithms. Okay, you tested your algorithms. You proposed some in fact some theory about that, and after you did a lot of experiments. Okay, and I know how it's difficult to do a lot of experiments with a human aspect and also with a computer aspect. So it's a very, as it was mentioned before, a multidisciplinary aspect. So again, third congratulations about that. So I have a lot of congratulations about that, and for me, it's I'm very pleased to discuss with you today for your work. As it was mentioned before during the two previous colleagues, in fact, okay, so a lot of questions have been discussed just before, and sorry if I continue about that, okay? First of all, okay, so you consider DBS camera like Prophecy, okay? It's a very nice camera, it's a very interesting camera. It was in dynamic. We don't speak about that, okay? Dynamic, I speak about the number of grade levels that you can obtain with this kind of cameras. Decibels in signal to noise ratio. So it's the first advantage that I can see in this camera. Okay, and about the speed of this camera and about the number of events that we can produce per second. If I remember, it's something like more than 1 million of events per second. Okay, and the problem that you had to solve during your thesis, during your PhD, it was how to reduce this number of, in fact, of events. So it's crazy, in fact, because you have a very efficient image sensor, okay? And after that, you have too much, in fact, events to process, okay? So maybe, in fact, I'm sure that 1 million per second is very interesting in some specific application, as I mentioned in my report, like in high energy physics, okay? So why not in very fast lasers, like for the Nobel Prizes during these last weeks in Physics Nobel Prize, okay, that they obtain. So maybe it's very interesting about that also, and I'm sure it's very interesting. But in fact, as it was also mentioned, maybe in real life, we don't need to process 1 million event per second. I don't know. We have some specialists here in neuroscience. Maybe it's possible to do that with our human brain or with eye. I don't know exactly. Okay, but my question is, because it was discussed before by Timothy, okay, and how much, in fact, events we need to process, okay, and I don't want to continue to come back again on this question, but my question now is, do you have an idea of what should be the minimum of events that we need to do some specific application like classification or segmentation, but we can stay on a classification task. So that is my first question. Maybe it's a difficult question, but I have no the answer. Okay, so
thank you very much for all your initial comments. First of all, and yeah, that's a really interesting question, and and I have a beginning of an answer because there was recently a paper that was published actually at the event-based vision workshop at CVPR 2023, where they tried to assess on so it was on a localization task where they tried to localize cars in event data, and they tried to assess how much events make a car and how much events make an object. And this was, I don't have the numbers right now, but there is this study that was beginning to go towards this subject. And it is actually really interesting to take a look at this because there is another study by the group of Scaramuza that recently discussed on the fact that the bigger the event camera, the information is not proportionally as interesting as the size of the event camera, because they showed that for different classification tasks and other tasks as well, for smaller event camera, they were able to do something with similar or even better results than with a bigger event camera. So I think those two studies combined shows that we should actually ask ourselves, should we still continue to make bigger and bigger event camera, or should maybe try to reduce it in order to focus on the maybe temporal precision and try to really assess how you said, like how much events make an object, how much a human being understand from those these few events. This is very interesting. Yeah.
Because I'm sure, in fact, that we could have after your PhD, okay, discussion about that and with some specialists about that, because maybe there is a ratio between the spatial resolution and the time resolution, because I'm sure that if you have a higher resolution, spatial resolution, maybe there is a ratio between, in fact, the high spatial resolution, like our eye, okay, and the time resolution. So maybe there is a discussion about that. Okay. I have a second question, a technical question that I mentioned in my report. It was about, in fact, for the science detection. Okay. And in fact, it's a good idea. So you explore, for example, the winner-take-all or clustering. Okay. And in fact, in the literature and the technical aspects, there were a lot of different clustering algorithms. So for which reason did you have this choice of algorithms?
I think it's a really interesting question as well. Just there is Riyad that is joining us on the Zoom. I just wanted to admit it so not to wait too much. Okay, you should be here. Hi, Riyad. Okay, it's connected.
Go ahead.
Hi, perfect. We can see him. Hi. Okay, so to answer your question, it's a really interesting one. So I chose to use the winner-takes-all for two reasons. The first one, it is a bio-inspired algorithm that is really easily implementable with SNN, and that makes sense when you take a look at the behavior of spiking neural networks, at least to my sense, and shows really interesting results. Like we do manage to detect saliency, so it is bottom-up saliency, but really interesting saliency, and we have demonstrated with our result that it is still to be quite accurate, especially when we try to apply this exponential mathematical formula to try to cluster those together with a specific distance and allow for multiple or not activation in the layer. So it was a way to really easily play on this letting through or not events in the layer in a bio-inspired way.
Okay, so maybe I should have to precise my question, in fact, but I don't want an answer from you about that. It's just a comment. In fact, my question was to consider, in fact, the implementation, in fact, the complexity of this kind of algorithms. My question was that, okay, if it depends of, in fact, complexity of performances and so on. Okay, so maybe it would be interesting to explore this question and to see if there were more efficient algorithms in words, in fact, of performances and complexity reduction. Okay. Let's say about the implementation now, because you spoke before and you answered some questions about the power consumption.
Yeah.
Begins to be more clear for me after your presentation or oral presentation, but I have again a question about that. It was on your slide 33 today. I don't remember in your paper page it was.
Get it back. Is it this one?
Yes, this one. Okay. So maybe I had the answer before in the previous slide that you presented. Okay, because there was a question between, in fact, energy and power consumption, energy in joules and power in watts. Okay, and my question was, in fact, if we see the bottom table here, so we see that we have more than 22 joules. Okay, and it means that it's a total consumption or total energy that we need.
Yeah, we managed to estimate that with the function provided by Spinnaker. So
yes,
this was the higher level of information that we managed to get.
Yes.
So this 22.3 joule and 22.7 is correspond to the energy consumed during the runtime only,
Yes.
and the other line, correspond to the initialization part of the network on the board,
Okay,
and
so,
the final line is
so if you understand, it's the full energy consumption is more than 22 joules. Okay.
Yeah.
So it means that in watts, if we consider 1 second, it means that the power consumption in 1 second is 1 watt. Okay, something like that. Okay. So there is a general question. I think that Timothy mentioned that because we have to have maybe a comparison with maybe I'm not very I don't exactly agree with that, but we have to consider, in fact, Jetson modules like embedded GPUs, okay, like Jetson modules and so on, in comparison with this kind of device, okay. And so maybe it should be the future, okay, to have a discussion about that, because we have to consider that. But in any case, it's not ultra low power energy, because here we speak about some watts, okay. And in fact, in my opinion, we need to consider maybe some milliwatts, something like that, because in fact, at the beginning, we have an image sensor. Power consumption is something like 10 milliwatts or maybe less, okay? And after that, we have a higher power consumption. So that is, it's very crazy, because the eye is very low power consumption and the brain is very power consumption. So there is maybe something which is difficult to discuss about that, okay? That is a general comment. So my answer, okay, I understood that. Now it's something like 20 watts or something like that.
Exactly. And this is the estimation on Spinnaker, but as I showed you in the previous table with specific comparison between the different boards, yes, Spinnaker seems to be the one that uses maybe the most energy yes, when we compare to Lowy or, for example, Kraken.
Yes, but maybe it should be some more than 1 watt.
Yeah.
Yes.
So maybe interesting to also look at isomorphic hardware, but we specifically took a look at Spinnaker because within our previous 3D project, we had to. Yes. It was in the use case to use Spinnaker. Yes,
I'm sure now, because there is about my previous question. So there is a combination between the number of events, okay, and the power consumption that is very important to consider this, in fact, event reduction. You are right about that, okay. Last question, if I have time, okay, 2 minutes.
Yeah, 2 minutes.
Okay. In fact, I fully agree. We also, for the comparison between ANN, okay, and SNN. Okay, so it's very important to have some answer about that. And again, it should be very interesting to have some scientific progress about that, to have in fact some answers. But I'm sure that if we consider, for example, your application for coastline detection, in fact, or maybe also for lip reading. So, in fact, what should be very difficult for even comparisons is with not with deep learning, but with only computer vision, very simple computer vision algorithms. You can, in fact, reach some good results with very simple algorithms like F transforms and something like that.
Yeah.
So maybe just a suggestion should be to consider more complex application.
Okay.
Okay, because if you have a comparison with this kind of application, maybe with very simple, in fact, computer vision algorithm, it should be more efficient.
Okay.
So thank you again, and all my congratulations, and also all for all your publications. Thank you.
Thanks, Michel. So we will now move to the questions of the examiners. So we have three. We will start with Elisabetta Chica, then Yulia Sandarmiskaya, then Riyad Benesman, myself, and then I will give the remaining time to your two supervisors for concluding words. For Riyad, who joined us, I just remind the game rules. As president and timekeeper of this jury, so you have all 15 minutes for your questions. So you can start. We'll start with Elisabetta.
Thank you. And thanks, Amélie, for the very nice presentation. I really enjoyed your work. As my colleagues already mentioned, there is a lot in there, and it's really timely. So I was really impressed by the breadth of your work and approaches and algorithms. I think most of my questions have been touched already in some or another way. The first one I have is about this reducing of the sensory data. You gave us a motivation in your presentation by showing an event-based sensor that has a high resolution, which is not the one that you used, yeah. And so basically what you're suggesting is the sensors are going to higher and higher resolution, so we have a problem because there is a lot of data. So I propose how to reduce this data so that we can do efficient computation. Now my question is, what do you think if I instead propose, okay, let's use low resolution sensors? What do I lose? What do I gain? What is the comparison of the two approaches?
Thank you for your comments and for these interesting questions. This is really interesting, actually. So I already mentioned earlier the work by the group of Scaramuza, where they demonstrated that smaller sensors seems to provide more interesting information for specific computer vision tasks, most computer vision tasks actually. But for my part, I believe that so between small sensor and the event data downscaling, maybe using smaller sensor would be more interesting because you won't have the intermediary step of downscaling the data. But this event data downscaling, I think in any case, are useful tools for existing dataset that we use as benchmarks that can be more run more easily for other tasks and other like it is more easy to actually downscale existing dataset than recording exactly the same with a smaller sensor. This is the first part. But if we take a look at our other contributions, so visual attention and neuromorphic foliation, those two, I think, add an additional information than the smaller sensor would, because for those two, we really have this attention, I was going to say, the specific focus on what is interesting. And even with smaller sensor, you don't have that. But there are some sensors that are currently being created where they try to have actually this visual attention model embedded in the sensor. So I think that would be really interesting to compare our results with the result we could have with those new sensors that are coming in right now.
And don't you think that, you know, the choice between different approaches in this case is also highly task related? For example, if I think about your coastline
That's true.
example, I would say, do I really need a very high resolution? Do I really need to go through the pain of having a lot of data, then reducing it, and then approaching the task that I'm at?
Yeah, you're totally right. That's a really a good additional comment. It really depends on the data set, but yeah, on the page and computer vision task that you want to achieve.
Thank you. Somewhat related, in chapter 6 and in your presentation, you showed us the first attempts to do this downscaling, and later on you showed a more complex way of doing it. We have discussed this already quite a bit in the various questions. One question that I had is that one of the problem that you mentioned is that the outcome depends on the dividing factor. So you always have some constant factor that is deciding how you downscale things. And in the second example, you went into an adaptive way of approaching the problem, but as it was already mentioned, this adaptive way is really a different thing. It doesn't compare with the initial part. So my question is, have you thought about making the first approach adaptive? Have you thought about mechanisms to dynamically adapt your whatever dividing factor to the current data, to the current stream of input data?
Okay. We did not think about that, but this is really interesting type of research, yeah. That would be very interesting, but I think we would have to find a way to do it adaptively during either the recording, if it is on an embedded system, or the processing of the data. And I think it might be a bit of a challenge to find out how to do that with the less possible, and while not losing important information while we are trying to adapt to this data. But this is, yeah, a really interesting path to take. Yeah. Thank you.
Yeah, you're welcome. I agree that it's challenging, but yeah, you would have the advantage that, you know, you have to decide the scaling factor on the basis of the statistic of your input, and then it's not going to be optimal for, you know, if you have a wide range, you're going to sit in the middle, and so you're going to lose a lot at the extreme. So that's why I think it would be a good thing to look at. And as I said, it's totally different from what you have been doing later on with the attention. So I think the two things can be complementary, and they can enhance each other.
Yeah, that's true.
I have a question about the tables that were already shown, but interesting enough, it's a question that wasn't asked yet. These two tables, they are in chapter 7. It's 7.4. Yeah, exactly. Those two. So you convinced us that the number of spikes is a critical factor for power consumption in relation to synaptic operation, because if you have spikes, you're going to have synaptic operation. And so if I look at the numbers on the table above, I have the impression our approach is doing quite well, because despite having a lot of synapses, you have not only a few neurons, but you also have a factor 10 less spikes.
Yeah. So
when I see the first table, I have high expectation for the second one. Can you explain me why these high expectations are not met when I look at the number of the power consumption?
This is a really good question. So I'm not sure I can actually explain how, but we wanted to pursue on this implementation on Spinnaker, because for now it's just an estimation of the power consumption, and we are working on the actual implementation and validation of the results we obtain. This is one of the few steps that we are still working on right now. And we believe that with the actual network, this might be more interesting, this result that we obtain. But this also led us to maybe considering doing a specific review of the energy consumption of Spinnaker and maybe also boards to really assess, is this, so as I showed you earlier, there is the energy consumed per spike, but I think depending on the board, it consumed different energy according to the neuron, as well as the number of neurons initialized. And this is something I wanted to pursue in future hypothetic words, either during my postdoc or maybe Hugo was taking a second PhD, and that was one of the co-authors of this paper would like to work on as well.
Thank you. I have one last question. I would like to hear your opinion on the neuromorphic MNIST datasets, and specifically with respect to the fact that in MNIST, information is not temporal at all. And in the neuromorphic MNIST, there is a temporal component, which in principle doesn't bring any information. What's your view on this?
I agree that an MNIST is maybe not the most interesting neuromorphic dataset that exists, but it has a huge advantage of being a neuromorphic adaptation of a dataset that we are often using to benchmark standard machine learning algorithm. And this is like a really famous dataset, so that is why we took it. But we believe that the results that we obtain with an MNIST are with either diverse gesture or with specifically more, for example, DTT17 or potentially the megapixel dataset, etc. Because, as you said, the information is not temporal, and the temporal aspect was added because in order to actually register the events, you had to move around those numbers. And the event data is not really interesting for that. It is interesting where there is a motion that adds a specific information in addition. And Spinnaker, spiking neural networks as well are really interesting to process temporal patterns. And I think that, yeah, indeed, NMNIST might be more interesting to be processed with standard machine learning algorithm than with SNN. But yeah, we use those results in any case because it is a benchmark dataset commonly used, and yeah, this way.
Thanks a lot, and congratulations again for your work.
Thank you.
Thanks, Elisabetta. So now we follow with.
Yeah, let me see. Can I still hear you? Can you hear me? Yeah. Okay. Yeah. Okay. Great. Okay, so I joined the others in congratulating you for having done a lot of work. Really impressive how many different things you've done. So with my questions, especially to the end, I'll try to tie it all together and see how it all comes together. But I will start with the very specific questions, partially understanding questions on my side. So I'm really curious, what exactly you have done. So I will dive into a bit more details to start with, and maybe we could also go to the slides. Like for instance, on slide 15.
15, okay.
1.5.
So 15, you said? 1.5?
Yeah. So there were some videos of the performance of this one of the downsampling techniques, or maybe even a couple of them. No, maybe the previous one. Let's see.
Oh,
yeah. The one before. One that you had.
Okay,
before.
sorry. This one.
Yes, yeah, this one. So these are the 6 different methods, right, that you've used. And I wonder the ones in the middle.
Yeah,
for spatial downscaling, right? So the ones in the middle, right, they have really little output. Can you maybe explain a little bit why that happens? And what is, maybe you can, in a nutshell, what are the main differences between the methods? And what is your conclusion? Which one was better than the others? So which one would you recommend to use?
Yeah, of course. So I don't know how much details you want, because I have some additional slides with some specific illustrations, but I can try first to do it with my hands, let's say. So the spatial tunneling method is like a reimplementation of the tonic methods, the one that existed before us. We just updated it to remove all duplicates. That was not the case beforehand. For the event count, we try to do a normalized event count. So we try to estimate, okay, we want to reduce a region, for example, of 4x4 pixels into 1 pixel. And we estimated if there were at least 4 events taking place in these regions, then we have reached our thresholds, normalized threshold, let's say, and we produce 1 event. So we did that for both polarities. And for the log luminance reconstructions parts, there's the methods that were with which the results were the most surprising, let's say, because for the log luminance reconstruction, what we did is that we, with the help of our collaborators at IMSC that are researchers in microelectronics, we tried to reconstruct the log luminance that was recorded by the sensor at each pixel when the dataset was recorded. So we really reproduced that at each pixel. And then, so we do that either linearly or cubically, so saying we reconnect the events with lines or with a curve, let's say. And then we calculated the mean of all those log luminance. And from this mean, we get the events that are produced. So from this mean, we try to take a look at where it crosses the theoretical sensor thresholds, contrast thresholds, and produces new events. So this is theoretically the method that is the most optically coherent, so the most coherent with the microelectronic hardware. But it provided really results that were quite surprising, because since we were doing this mean, we really have like way fewer informations. So yes, this was a bit surprising, but we can see that since this is also the one that takes one of the ones that takes the most time, we were like, okay, this exists. It is interesting to take a look at what it provides, but maybe you can go another way, such as, for example, the event count. That is quite interesting because it runs on the computer really quickly and provides information that is way less saturated than the spatial tunneling. And for the homomorphic parts, the SNN pooling seems to be the most interesting. So you'd still need to have a bit of hyperparametrization to really adapt it to the data and optimize the number of events that you produce. But those are quite interesting because when you look at the behavior of spiking our network to the behavior of the log luminance recorded by an event-based camera, the behavior are a bit similar. So from an optical point of view, it is coherent to compare those two together. And we also showed in further results, for example, here, that the accuracy that we obtain with those methods are the most interesting ones. Even more interesting than special.
Yeah, thanks. Another question. So the cost of these algorithms, did you try to compare that? So, how much time and energy do you lose on kind of reducing the number of events?
I did. We did a comparison of the time it will take, and just take it. Yeah, it is. We did a comparison of the time it takes to actually reduce event data with those different methods. So this is like some results that shows that depending on the method that you use, you do not take as much time for each method. And for the spatial downscaling, the event count and the spatial tunneling seems to be really the most interesting ones. We try to assess the complexity of the different algorithms, and we presented some of those results in my manuscripts, but globally, yes, spatial tunneling is the less complex, so it's the one that consumes the less, but the trade-off with the quality of the data afterwards is really not that great. And finally, we also try to assess, but I don't have like the results here, sorry, I have the results in manuscripts. The energy consumed, the time it took for the SNN pooling methods to be run, because we implemented those on Spinnaker to try to assess how long it would take to run those methods, especially if we wanted to put those first methods as like a first layer before more complex networks that will do a specific task with those spikes that were reduced, those events that were reduced.
Okay. So what is your overall conclusion? Do you think it's worth doing this the number of events reduction in software, or do you think this is something that maybe one should take care of somewhere closer to the sensor before the events even leave the sensor? Because if you imagine, like if you have one of the sensors with very high resolution, there are a lot of events that you have to ingest on the computer and then run these algorithms. So in your experience, do you think it's a viable pathway, or one should have this event reduction taken care of closer to the sensor in hardware maybe?
I think it really depends on the application task, first of all. So yeah, it will be really more interesting to put it closer to the sensor, that's true. But we want, in future works that we could do to really further complete those results, we would like to assess on an embedded system if it is doable to actually reduce using those different methods before giving the event as input to an embedded SNN. For example, for the coastline detection task, that would be really interesting to put that into action. All in all, I think it really depends on the task that you want to do. If you're like on treating a data set that you already have recorded and you're on your computer and you want to have global information with no need for specific region of interest, maybe the event count is more interesting. Or the spiking or network pooling are really interesting if you are already using SNN and you want to combine those two together. I think those two are the most interesting one for the spatial reduction. And for the temporal reduction, the structural method seems to be really interesting in terms either of timing and of quality of the data that you keep.
Okay. Another question, like trying to tie already this part with the application part. So did you try to use this method in one of the tasks, maybe lip reading on one of the other tasks, and see how this reduction of number of events influences accuracy of your task performance? Did you try to apply these methods beyond only gesture recognition data set?
So we did apply those methods to, so if I remember well, we did apply that to lip reading, especially because in order to run our models, it was way more interesting to have smaller amounts of events in order to allow for the model to run quicker and with more efficiency. So we did apply that, but we did not have the time to make a really complete comparison with the different methods applied to it and the method that the result that we will have without applying that to the lip reading model. But this is something really interesting, and we would like also especially to apply that to the coastline detection model, since we are currently working on a demonstrator within Apolis 3D. It would be really interesting to apply that, to add this additional step of event data reduction and see what we obtain with that.
Okay, cool. All right, then I have a bunch of questions to this human study, right? So if you go to slide 22, so you have this dividing factor, right, for humans that you did for humans. So I wonder how it relates to kind of the previous factor when you described your kind of the models that you used to reduce the data, the number of events. Seems to be a different factor, and maybe you can comment a little bit. So what is your conclusion? It seems that the people fail pretty quickly if you reduce the resolution of event-based data. Is it correct?
Yeah, so to answer the first part of your question, those are the same factors. So this is the same way so that's the same values that we applied to the original ones. It's the same way of reducing the data. So the values mean the same. But indeed, for example, on the spatial dividing, we limited ourselves to 10, reduction of 10. And to the temporal and different temporal methods, we took different reduction factors because we had we wanted to select certain dividing factors because we wanted to keep the task as short as possible for the human volunteers in order to not make them lose their concentration and then reduce the quality of their performance over time. Because if we had to take all of dividing factors, all of our methods together, we believe that it would be like way too much for them to really like stay in front of their computer during 1 hour and doing all of that. Like at the end, they would just lose concentration and we'll have like falsified, let's say, results, biased results.
So what was your overall conclusion from this study?
So from this study, we saw two main conclusions, let's say. Like one main conclusion, I say. The first really interesting thing that we saw is that human beings do not understand even data as machines do, really not at all. I have many of the volunteers that I knew came to me afterwards saying, okay, I did not understand what was going on at all for most of them. And it was really interesting to see. So there was first maybe a bit of bias that they are not used to using event-based camera, but we can also see that the machines like understand visual data really differently from us still. And it is like really interesting results to have and really interesting insights, especially for this novel field of research that is even neuromorphic computing, I say.
Yeah, I think this is particularly interesting for neuromorphic because it's supposed to be biologically inspired, right? We're trying to model human perception. Yeah, so I think that's indeed an interesting insight. Yeah, which needs to be maybe discussed and looked deeper into in the future. Okay, another quick question. So in your attention model, right, where you had these multiple objects, so you had the winner-take-all structure that was contributing, and then you had the threshold adaptation. So maybe you can comment a little bit to which role threshold adaptation played in this algorithm, in this system. Yeah, and how important it was. I think so. Okay. Yeah, I think that was this one. Yeah.
Was this a multiple object of interest selection or the one object of interest selection? Because it's not the same threshold adaptation.
I see. Okay, then maybe you could comment on both briefly.
Yeah, sure. Okay, let me just find the first one then. Okay, so for this one, for the selection of only one object of interest at a time, the threshold adaptation rule was really important, let's say, to this selection, because thanks to this threshold adaptation rule, we are able to put like a kind of mask on the output layer, like hindering the activity in the output layers at the places where the saliency detector considered that it was not interesting to activate. Okay, and this was done by increasing the threshold to a maximum value, so that the membrane potential had more difficulty to reach that. And so this way, the neurons will not spike if there is the threshold that is really high. And where the saliency detector was saying, okay, this is interesting, there is activity here, the threshold will be reduced to really close to the resting membrane potential value in order to facilitate the activity. And we try to implement these mechanisms with weights instead of threshold adaptation rule. But if we implement it with weight, like with maybe just like standard activation, saying that if there is activity in saliency detectors and we are activating this specific part, we lost the details in the object of interest. There was like just this whole region that was heavily activated, and that was the issue that we had, especially with low E, because with low E we could not implement the threshold adaptation rule. And so we had this issue of losing the fine details in the object of interest in the output layers. And this helped us to keep the details.
I see. All right.
And for
yeah.
The multiple one, I'm going to put in big side. Yeah, okay. So for this one, we tried to adapt the previous threshold adaptation rule, but this time we had to take into account the lateral activation additionally to the saliency detection activation, because we wanted each output layers to let through events that were not already let through by a previous output layer. So this, so if we take a look at each of these rules, first we take into account the activity of the saliency detector by first, in the first step, decreasing the neuron thresholds if there was activity, or increasing it if there was no activity, it's the same way as before. But then additionally to that, we took into account the lateral layers and synaptic spikes, from which we calculated the lateral activity. And then we combined those two together with a sort of mask saying, okay, if there is activity in the lateral layer, but the threshold is low, we're going to put it really high in order to hinder the activity, because we don't want to have activity in the same regions in two different output layers. I hope it's
And then how did you implement? So when you talk about this mechanism now, you say like if then, how did you implement it like in the neural network?
So I implemented those models using the Pine interface with the NES simulator. And this interface is really interesting because it helps us to implement specific adaptive rules that can be called at each time step. And so really at each time step, we had this if-else applications, like specifically with NumPy arrays and masks. So yeah.
I see. All right. I think I'm running out of time, so I'll maybe pose the last question. Kind of more conceptual one about the usefulness of neuromorphic computing, right? So you said this was one of your conclusions, neuromorphic computing is really useful in this field. Can you maybe name like a concrete example where you have seen like SNNs were really the ones that brought now, performance boost to a task compared to, just running some algorithm, which is maybe not even deep or neural network based on a microcontroller, something that people do in event-based vision quite efficiently, or having a deep network, right? Solving the task by collecting event images and then just running SNN over them. Also state-of-the-art systems use this approach, right? In Davide Scaramuza's drones, for instance. So can you maybe give us an example where you saw now SNNs are really the ones that make for excellent performance here?
So on top of my head, I have an example that is maybe not extremely convincing, but still quite promising. It's an example we worked on, so that's why I'm thinking about it right now. It's a lip reading task because there existed, so we were the first to implement a neuromorphic end-to-end lip reading model, but before us there existed an ANN model applied to event data for lip reading. And we compared our results to their results, and with a similar amount of neurons, we were able to have an accuracy that was better than them, if I remember well, our results. Sorry, it's a bit far in my head. So this was quite convincing. So when we did a comparison with that.
And you compared, I just missed acoustically, you compared the energy or did you compare the accuracy?
Sorry, it's a bit far. I think we compared the accuracy to them. Yeah. And we separated the energy consumed with like the number of neurons. Saying, yeah.
Right.
Did like a large interpolation. So yes, this is like one example. And right now, I'm sorry, I don't think for anything else, but since I come from biology, I'm really convinced that spiking neural networks are really promising because this really comes close to what us human beings are able to do, or even just any animals are able to do really huge things with small amounts of neural networks that can be implemented with spiking neural networks. I have the example of insects, for example, and this is able to do that with really low energy consumption. And with ANN, we are not yet able to implement things as amazing as that with such a low energy consumption and low amounts of neurons. So personally, I'm quite convinced because of that. Yeah.
Yeah. Okay. Thank you. Yeah, I guess we all agree with that, but I think it's good to have a debate about that once in a while, and make sure we really apply SNNs where it makes sense. Anyway. Yeah. Okay. Thank you very much. I'm done with my questions.
Thank you, Julia. Riyad, floor is yours.
Yeah, thank you. Thank you so much. Thanks for the invitation. So I'd like to, so I've followed your PhD, right, in the following committee. So I think I know a lot about what you've done and asked you all the questions. So I won't be asking more questions. This is really nice work. You've done a lot. You've implemented a lot. So I have one question for you. Now, you see event cameras are a promising thing. What was the biggest difficulty if you had to take any of this to use it somewhere? Where do you think the problems are to make a product from what you have? What was the highest difficulty you had to cope with?
So, sorry, could you repeat your question? Like, what do you think of like difficulty in terms of implementation, application to real life scenarios, you mean?
Yeah, I mean, this work is nice and lots of people work on saliency, etc. So I'm just asking you, and I know you've seen a lot and you've done lots of implementation, you've seen hardware, you've been in the field for such a long time. So my question is, what was the main problem you had to encounter? If you have like a magic wish, say, if I wish I could solve this, this, and this in my life, I'll change the world or whatever. What was the highest problem you had to face during all this PhD that really bothered you and prevented you from doing what you were doing here?
That's a really hard question.
Okay.
I think I would have liked to, but once again, it's because I have like biological background. So as I said earlier, I'm convinced that we can implement what human brains can do with spiking neural networks. But I think what is missing is actually the biological knowledge. So if we had like way more knowledge about this, we could be able to implement way more interesting things with spiking neural networks and do some really amazing things for artificial intelligence with low energy consumption.
I see. So you think it's missing knowledge, basically?
Yes, still a bit, but we are working on that. And I think that's really interesting with this field of research, that we are able to work on similar things from biological point of view and computer vision point of view. And it was especially interesting when I did some research on delay learning, because I saw that it was like a bit of axis of research that was pursued by both computer vision persons, so in SNN or other stuff, and both by biologists to try to understand what was going on, and kind of parallelly. And it was really interesting to see that both results can help on the other side. So yeah.
I see. And sensor-wise, the sensors are perfect. You were super happy with them. You don't want to change anything there.
Okay, yeah. I think maybe, but I think this is like current ongoing work. But what is something really missing in event-based vision is the color part, obviously.
Is what?
The color part, the visual information on colors. But I think since event-based to implement, like it is a really different way to implement visual information. But I think if we could try to find a way to have a compromise between those two while still keeping really low memory data, low energy, that would be really great, and we'll be able to have even more interesting results.
I see. So basically you're telling me you're complaining about the loss of things like photo consistency and everything people have in computer vision that allow them to work, right? So you want to add more features like color. Do I understand correctly? Yeah. I see.
Yeah, for example, that would be really helpful.
Okay, well, listen, thank you so much. There's been, I don't want to make you the insult of asking you any technical question. I think I followed sufficiently this work. Nice work. It was nice seeing you at the workshop. Can I ask you what you're going to do next?
Yeah, sure. Oh, yeah, the presentation. I'm doing a postdoc that will begin in December 2023 at the IMS lab with Sylvain Saïbi. And we are working on the Green project, the Green AI project for edge computing and multi-neuromorphic sensor fusion. So still with the aim of AI with low energy consumption.
Sounds amazing. Well, say hi to Sylvain, and thanks so much again for your PhD and presentation.
Thank you.
Thanks, Riyad, for saving time.
Thank you.
So I will now give the floor to myself, and I would like first to thank you for your nice presentation. Clearly, it was dense, but it was also pedagogical, so you made a good choice for, I think, for your presentation, the amount of work you did. And as my colleagues, I was impressed by this amount of subjects you have treated during that time, and also the number of internships that you co-supervised. It's amazing to see that you co-supervised something like 14 internships, 9 on one subject and 4 on another, or 5. It was but something like 10 internships in 3 years. It's impressive.
Thank you.
So I really appreciated the idea you explored. We had few interactions, very few interactions in the past, but I suppose that you know that I am convinced that adding such concepts of attention and progression are important properties. in our domain of neuromorphic computing, at least because it is the way the brain works, and it is still interesting to replicate it in order to better understand how it works, and but also because it can be a strategy followed by nature in order to have a low power brain and not to process all the information, but only the relevant one. The big part of the question is what is the definition of relevance, and is it related to a specific task, and perhaps not relevance by default or generate definition of relevance. We had a discussion on the fact that I had preliminary works on the association of silencimab, dynamic neural fields, and supervised spiking based classifiers onto a sensory motor camera, and not onto a data set that has been already registered and stored. So my first question is related to the behavior of the silencing model you proposed, the spatio-temporal filtering, and its behavior at longer time scales than the one of the device gesture samples. Because device gesture, you have small samples of a few seconds that are repeated along the time, but how the selection of ROI of the region of interest behaves at longer time scales. And specifically, what if you have more than 2 ROI? Yeah.
Okay, thank you for your question. Very interesting. So yeah, as I did not go too much into details into this model, but it is a bottom-up implementation of visual attention. So this is not specifically correlated to any computer vision task, even though we believe that it would be interesting to implement some other kind of way. So this is quite interesting that there will be those CIFRE PhD project afterwards working on that. So this model that we implemented, it is bottom-up and considers that with the intrinsic behavior of spiking neural network, it is able to detect things interesting. So the things that are considered interesting are the regions with a high number of activation in the small spatial and temporal region in the sensor. And for this, we began from the initial hypothesis that the human being would think that with a bottom-up situation, so with no external task, we believe that yes, this is the most interesting thing in the event data. And we would have loved to be able to actually assess that, so measure what which places human gaze goes for the different event data set. That would be really interesting. Sadly, we did not have the time to do that, but we would have loved to do that as a way to complete this model implementation. So the second part of your question, so we applied these attention mechanisms to the DVS 128 gesture dataset, where at each time you have only one region of interest, let's say, which is the hand that are moving, maybe 2 if you have the 2 hands. But we also applied it indirectly to the DDD17 dataset with a foliation. And finally, we especially, so this is work that was conducted with our colleagues at IMRA. We applied it to the private pedestrian dataset that has longer frames, longer samples. Okay. So with the help of our common intern, Hugo Bilzemi, and we saw that this attention model mechanism on this long sample still is able to process, so to identify multiple regions of interest, not only one, not only 2, but multiple at the time. So I'm speaking about the detection of region of interest, not the output of object of interest. But it is able to really detect different places, and it really helped in the pedestrian localization. It was really, you get really accurate description, and the pedestrian, since it was sorry, not a mobile, but a fixed camera, the pedestrian actually high activations of events, small regions of spatial temporal in the sensor. And on the longer time, it was still provided us really interesting results. Okay. So yeah.
Okay. related to my previous question, I was wondering, in fact, if the way you implemented your spatial filtering filter, is it far finally from a dynamic neural field? Because you have inhibition in your system and you have the notion of time, and so did you find all the properties of a DNF?
It comes close to a DNF, and actually we compared, at some point we compared results with the paper from Renner and colleagues in 2019, where they did implement a DNF, if I remember well. I think the differences are maybe in the architecture of the model, where us we reduced the saliency detection part. And we believe that it would be interesting to try to further research into DNF, the different, as you said, features of a DNF, and try to see if we can manage to have better results if we further go into this direction or not. But sadly, we did not have the time to go further into this direction.
I can understand. Okay, and in the case of multiple regions, so you have an inhibition between the different the different models in order to have different regions of interest and not the same, as you explained. So in a certain way, it's is it something similar to the inhibition of region we can find in some saliency models from Treisman or IT, but that is proposed as a sequential process, and you are proposing a kind of parallel inhibition finally, where you could follow and track several targets simultaneously.
That's a good question. Sorry, my bibliography in this specific part is a bit far, so I trying to replace the inhibition part.
You know, it's the process that helps you to inhibit a target that you already followed in order to go to the next one, and not coming back to a target that you already focused on.
Exactly. Yeah, we try to implement kind of a similar way to do so, with, as you said, lateral layers. And especially we try to implement that so with different architectures of the network. And here we have this architecture where we use threshold adaptation rules instead of lateral inhibition with like synapses inhibiting, because we thought that we had way more interesting results with this threshold adaptation rule than with the lateral inhibition. So yeah, started from this idea and try to adapt it to make it work as best as possible.
Okay. And why did you choose to move finally from the original mechanism of where the brain is only has only one region of interest and one formation in a certain way? So what is the reason to go in that direction? Is it it would be perhaps I would say an overhead in terms of power consumption, perhaps to get a system that would be able to follow different regions simultaneously?
That's the question as well. So we have two main reasons why. So it was many contextual reasons. So the first part is, as I said, this work was done with our colleagues at ETH Zurich, so with Michele Magno. And Michele was specifically interested in having this multiple following of object of interest at the same time. So try to see if it was possible, and then ideally in further steps try to have it without this additional number of neurons, because this is indeed like an issue with this model. And the second reasons of this choice of multiple regions of interest instead of only one is because of the electronic foveated event-based camera that is developed by our collaborators at IMSC. On this camera, you don't have only one region of interest and then lower resolution, you have multiple objects of interest. So I try to mimic human eye with multiple fovea instead of only one. So they go beyond biology. And so that's why we needed to have this model where we could have multiple regions of interest at the same time.
Okay. Second question, I was also wondering what is the cost of the overhead of the features you propose in the processing architectures. So the three of them, in regards to the gain obtained in terms of reduction of the number of events. So I think it was the sense of the question from Julia, but you made a kind of ablation study by measuring the same network without the downscaling or without the foveation in order to measure the difference in terms of the global behavior and plus also the number of spikes and also the global energy.
So it is a really interesting question. This is one of our perspectives, actually. We began kind of to do that. So let me just show you some results. So especially for the visual attention part. So I showed you some results on the speed-free implementation when we tried to assess the cost it took to implement this visual attention that will be added to further processing. And we also did the same thing for the Kraken implementation, where we tried to assess in total how much fuel it would take to do so. And this is like first steps for further more complete assessment of the energy that we will save globally if we do this first step of downscaling visual attention foliation, and then apply that to another computer vision task. But this is something really interesting, and we believe that would be really, really interesting addition to this work. Yes. This complete comparison.
That has been measured on both Kraken and
Spinnaker.
And Spinnaker, okay.
Yeah.
So we can just ask the question if it would be interesting to have a specific hardware for this specific pre-processing phase compared to Spinnaker and Kraken that are, yes, clearly dedicated to spiking neural networks, but not specifically to the that kind of filtering in the visual field.
Yeah.
So that's also my last question. So we saw the energy consumption you measured and the different neuromorphic hardware, and on that kind of digital architectures such as Spinnaker and Kraken and also we know that the most important part of the energy consumption is related to the access to the memory, and not really, in fact, to the synaptic operations. And so in the brain, this cost does not exist because it comes directly from the strength of the connection, synaptic connection itself. So what do you think about considering emerging neuromorphic devices such as memory steal devices to implement?
Yeah, there's something that's really interesting because here we used only analog or no, sorry, we used only digital or mixed analog digital neuromorphic hardwares, and we believe that as it is said here, so this citation from on which we base our core research problem does say that, as you said, that this needs to receive to go get the information in memory and then rewrite it, all of that, and this is needed on digital, but on analog normally this cost should not exist or should be really reduced, and that's why we think that it would be so really interesting to make all those energy consumption assessment on this new hardware, and maybe that would be even a greater argument for stacking neural networks compared to ANN in this field.
Okay, thanks a lot for your responses, and I will give the last words to your supervisor. So starting with Laurent.
Okay, I am allowed to ask questions.
Yes, yes, if you want. Yeah, you have 15 minutes. You make all you want during this time.
Okay, so congratulations, Amélie. It's really a great work. And you really applied the optimization between quantity and quality in your presentation. It's really great. I know how painful it is to do a presentation. It's 3 years and 45 minutes. It's insane. So it's really the tip of the iceberg, and you really made a lot. Like Tim said, you went to software, hardware, and psychophysics, and more and more and more. So it's really great. I'll be frugal in my questions. age way. Just as a curiosity, and because I know you are interested in biology. So for the first part, you presented things in terms of results in computations and so on. So do you think the sparsity that is induced by the downsampling, the less events, is it something that is present in biology, like in a retina?
Not as you as expert, but I'm trying to answer like correctly. I would say I think like the event downscaling has been implemented like with the global, and that we downscale spatially. I think it does not really exist because it is more like the foveated actually system where you have less information overall because you have more information where you look at and not elsewhere. But I think it would be interesting to see if something akin to the SNN pooling methods that we have takes place somewhere in the brains, either for, so here we're looking at visual data, but I guess maybe it could exist also for like other kind of sensory information. That's a really good information, and I would really be interested to some bibliographical work on that.
Yeah, because from the 100 million photoreceptors, you go to 1 million fibers in a optic tract, so that's a compression, but it's also a good way to do biomorphism is to select the good features, and you did a very good work in doing that. And also related to the question of Michel on are there different models? You think with different levels of noise, perhaps the algorithm should change, should adapt? Do you need
do you mean between the, so are you still talking about the event data downscaling only, or like just the
globally? How many spikes does it take to make a giraffe looks like a giraffe?
That's also a good question to have, because as I answered to Michel, there is like some work on that that I know of neuromorphic, but in terms of biology, that would be sort of interesting to see what the brain does. Like, did we manage to assess that? I don't know, but that's really an interesting question. Yeah.
Is it more than a mouse?
But that's I think it's a feature hidden in your solution. Is that the more noise, the more events you will need to integrate information, and that's something observed in your retina. So I think it has more parallels to do, and that's hidden treasures. So on attention, so you related to the answer you gave to the question from Riyad on having a magic wand and making adding a new feature to the cameras. So if you had colors, it means that for attention you could do something that we do very easily. Is that you ask to a person to attend to something in space. They will do it even without moving their eyes. If you ask them to attend on the color, like blue, I will know that here there's something which should be blue without looking at it. It's blue, yeah. And so do you think you may do something similar in your model? Because you attend to one feature.
Yeah.
More things. Can you?
I think we could, add. I did not really think about how we could implement that, but maybe like either combining on the same mechanism, so maybe combining two mechanisms together to have like a middle results, but we have something that is able to detect, because so we are still on bottom-up visual attention model, and for that we know that the color that we detect in a bottom-up situation is the color that is the most different than the others. So maybe we try to implement something like that, something that where the information is encoded in a way that is really different than the others, and try to combine that together. That'd be quite interesting to have that.
More things to do.
Yeah.
And so now perhaps something a bit more personal, and then if I look back at the subject of the thesis, you don't do the subject at all. At the initial. No, the initial plan.
Initial one,
Yeah.
was, I don't even remember.
No, but it's
Yeah.
in the sense that it's very positive to. I don't think I hope the PhD students here will not take it as a guideline to do something different than the subject, but it's a show of independence and of independence of mind to be able to construct a subject from the initial conditions, and you know that especially with COVID and so on,
Yeah.
there may be some chaos. So it's positive that you didn't get everything exactly as planned, but you had many things that went. You had very good production, and what is very striking is that you had many collaboration with many collaborators, and which is kind of different from like the way of functioning of many people. And so my question will be a bit personal, is that now you are one step to being at another level. You're not here yet, but perhaps in a few minutes. Can you give an advice from your expertise of what is it to, and I know that in your extra academic life, you have many activities related to having collaboration and so on. Can you give one advice that you gain from having these many collaborators?
I think that's like a really huge plus for me to have that many collaborations, because I was able to do so many different things, and I really like that. I also managed to learn a lot of things because, for example, thanks to my stays at ETH and at IMC, I learned a lot about microelectronics because I didn't know anything about it at all beforehand. So it was really amazing with that. And I think like this was something I do not regret at all in my PhD thing, but this is like also a personal way of doing. I really like doing many different things. I like having many different subjects of research at the same time. I would highly recommend other PhDs to really go and collaborate and discover other things and try to see like a bit above the subject. But only if they're comfortable in doing that, and if they'd rather just stay on something, maybe collaborate, but with one specific person, I guess. But in any case, the collaboration is very interesting.
In any case, it shows that you like it. So yeah. Congratulations, and like the rep to the president. Thanks.
Thanks, Laurent. Last words from you. Okay. Thank you, Mr. President. Okay, Amélie. I have no questions, obviously, but maybe I can comment a bit. First of all, I would like to thank the committee members, and especially.
Sorry, I really need to stop you guys. I have to jump to a meeting. I'm sorry. I really have to leave. Talk to you all soon. Thank you. Bye. Congrats again. Well done.
Thanks for
I'll
coming.
send you my comments by mail. Thank you. Thank you so much.
Thanks.
Okay, so thanks to Riyad, and well, especially thanks to the reviewers, because it's always interesting to have like an external feedback, and we really need that. It's important for us to progress. And maybe I can also say a little disclaimer, because we had a full schedule for September, and Amélie is just back from sick leave. She just came back like 5 days ago to prepare the defense. So we had many plans to build on the comments of the reviewers and some extra experiments, and so this was not possible. So it's just an explanation, but not an excuse. So the work has been done. Amélie, you come from biology, right? And bio-inspiration was kind of a guideline in the work. This is probably maybe one of the explanations why we didn't do backprop after the comment of Tim. And also we inspiration from biology, and as you said, we wanted to go over biology with multiple foveation, right? So this, as it has been said many times, was done in the context of like an interdisciplinary consortium. And I think that you took the best out of this collaboration. I guess it's never easy. Interdisciplinarity is very hard. It's very hard to find a domain where each of the domain, if each of the discipline, like tackle some real challenge in each community, and not only have a kind of master-slave relation by using one domain to help another domain, but I think it was a very nice situation where the collaborations with INT, with IMSC, with ETH was self-enriching. And also you had the constraint of the use case of the project. So I'm sorry that it was like a stone in your shoe. You had to stick with this use case that was probably not the best. And you have to work for the project, for the demonstrator, and you also have to make some nice publications, and sometimes the objectives do not match. So I think you made the right choice to do the publications and work on probably some other project, but that fits your project, right? So you helped us to strengthen the relation with INT, with IMSC. So it's like we are here doing computer science, and INT are expert in computational neuroscience. In Zurich, we have some hardware architectures, and in IMSC we have some circuits for sensing. So it's a nice opportunity, I think, for the work that you have done. And your curriculum is a kind of trajectory from biology, and then bioinformatics in Bordeaux, and then computer science here, and then you're going back to Bordeaux for in IMS, right? To do circuits. Maybe you're going to specialize in that. In your next slide. And you have, as it was highlighted, you gained a real expertise in many domains. And I remember that in this very room, you once gave a tutorial on Spinnaker. In the project meeting, you gave this tutorial that was successful to the whole consortium. And that's where you came from far. and I think it's a very nice achievement, and you've been, to my understanding, you've been a pillar in this project. So it's I'm very happy, and I would like to congratulate you for the interdisciplinarity in your work. May I comment more? I have time. Okay, I could speak for hours. Just So maybe I can also comment on the hard worker that you are. As Laurence mentioned, you're not only committed to work, but you are also committed to other activity. You're a teacher, so a teacher who is much a skilled teacher, much appreciated from our students in the engineering school. You're also a supervisor of many internship students, as Benoit highlighted. Maybe I'll come back to that later. And also, you have taken some important responsibilities and role in the student association in the lab. And what surprised me is that during the summer break, you do not go to the beach like other students. You use your time to be the head of summer camps and work with kids. And I had to do some paperwork with CNRS, the funding agency, to allow you to use your time to work and to state that it was not impeding your work. So well, I'm wondering how you manage your time. And I also remember that we were at the end of your first year, we were summoned by the doctoral school, if you remember well. They said, what is going on? How is Amélie supervising so many students? It's not normal. Right? So when is she doing her PhD work? So we had to convince them that by supervising these students, you were doing your work. And it's not Master 2 level students, also Master 1, and some are like kind of assimilated to student projects. So not all of them are 6 months long. And so we had some, a great number of students, very nice students who helped us in this project. And so after Laurent comments about like choosing your way, since the very first day, I always told you that the PhD project is one of the only research projects where it's planned ahead to have a change of principal investigator sometime during the project, and you fully took your role in being your own manager, the project investigator of your own project, and you have always, or most of the time, made some very relevant decisions for your work, which is much appreciated. And I just want to thank you for all the work that you achieved, and I wish you the best, all the best for your future. Thank you.
Thank you. Thank you
very much. So it's time now for the deliberation, and so we will ask the people in the room to leave for the member of the jury.